Potassium, calcium, and iron are biometals that play essential roles in the growth, development, and day to day function of humans. Gadolinium is a contrast agent commonly used in magnetic resonance imaging, aka MRI, to enhance normal body tissue and highlight pathology. The purpose of this experiment is to study how gadolinium affects biometals in aged apples. We used an aged Fuji apple to conduct our experiment. Before adding gadolinium to the apples, we radiographed the apple to look for region with an abundance of iron and areas with a lack of iron. These regions were validated with an MRI scan. Wells were made at the 11 o'clock, 3 o'clock, and 6 o'clock positions. 5 milliliters of gadolinium contrast was added to each well, and radiographs were taken using a hologic mammography system. Additional radiographs were taken 24 hours later, 1 week later, and 2 weeks later. Throughout this time, the apples were left undisturbed. We used ROI statistical analysis to measure the distribution of iron. As the apple was not moved, we can ensure that the region measured was the same for every image of the apple. The initial radiograph of the apple showed iron tended to congregate around the apple core as it ages and dries, potentially more so around the pore walls. When gadolinium contrast is added to the aged apples, we see that gadolinium disappears from the well quicker in an iron-rich environment than in an iron-poor environment. After 24 hours, gadolinium does not leave any noticeable bright patches in the apple. However, we can see that the effect of gadolinium on the apple is an overall increase in brightness of the radiograph. Follow-up radiographs were taken 1 week later and 2 weeks later to show a continued gadolinium and iron movement. From these results, we can see that as the apples age, the iron concentrates around the core of the apple. When gadolinium contrast is added to the apple, we see a difference in the disappearance of gadolinium between the iron-rich regions and iron-poor regions. It is believed that gadolinium engages in transmetallation with ferric iron, which may provide an explanation for the rapid disappearance of gadolinium. This suggests gadolinium may not be as safe of a contrast agent as we had previously thought. We use gadolinium contrast frequently when imaging vulnerable members of our population, and it is thought that gadolinium contrast is a safe contrast. After all, our kidneys are able to remove it from our body. But our experiment shows that from the minute gadolinium is added to the apple, it already has an effect on the movement of iron in our body. It is possible that this may lead to disrupted iron biochemical pathways, which may lead to neurodegeneration.